Right now, at the center of our galaxy, there is something so dense, so violent, so fundamentally wrong with the universe's rulebook that time itself bends around it and slows to a crawl. We know about it, we've photographed it, and the more we understand it, the more unsettling it becomes. 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury, sitting 26,000 light-years from where you're standing right now, spinning, pulling, feeding, on gas, on stars, on light itself, and on the one thing none of us can ever get back: time. This is Sagittarius AS, the supermassive black hole at the heart of the Milky Way, and the physics of what happens near it will rearrange the way you think about every second of your life. To understand what a black hole does to time, you first need to understand what time actually is, and the answer is deeply uncomfortable. Time is not a fixed universal river flowing at the same speed for everyone. Einstein proved that over a century ago, and it has been confirmed so many times since that we now build it into the technology we carry in our pockets. Your GPS, the navigation app you use every single day, runs on satellites orbiting roughly 12,500 miles above Earth's surface. At that altitude, gravity is weaker than at the ground. And here's the strange part. Because of that weaker gravity, the atomic clocks on those satellites tick faster than identical clocks on Earth. Not by much, about 45 microseconds per day. But if engineers didn't correct for that difference, GPS accuracy would drift by roughly 10 kilometers every single day. Your navigation system would be useless within 2 minutes. We are already living inside a universe where time does not tick evenly. The question is simply how extreme the distortion gets. Near a black hole, it gets extreme beyond imagination. Gravity is the curvature of spacetime. Every mass warps the fabric of space and time around it. The Earth does it slightly, the Sun does it more dramatically. But a black hole, a true singularity, pulls the curve so tight, bends the geometry so violently, that the closer you get to its center, the slower time runs relative to everything far away. This effect has a name: gravitational time dilation. The mathematics come from Einstein's general theory of relativity, published in 1915. The stronger the gravitational field around you, the slower your clock ticks compared to someone sitting far from any source of gravity. It's not an optical illusion. It's not a perception trick. Time is literally running at different rates in different places. Now scale that effect up to a black hole. Imagine you could station yourself safely just outside the event horizon of Sagittarius A, that invisible boundary point of no return, sitting roughly 7.4 million miles from the singularity at the center. From your vantage point near that edge, you would experience time normally. Your heartbeat would feel steady. Minutes would pass. You'd check a clock, and it would run as it always has. But back on Earth, thousands of years would be rolling by. Every hour you spent near that boundary would swallow centuries of Earth history. Civilizations could rise and fall while you watched a single sunrise from the accretion disk's glow. The effect is not science fiction. It is a solved equation. The closer you are to the singularity, the more severe it becomes, and at the event horizon itself, from the perspective of an outside observer, something truly strange happens. Time stops. Not metaphorically. According to the mathematics of general relativity, any object falling toward a black hole appears, from the outside, to slow and then freeze at the event horizon, permanently. The light-carrying information about that infalling object gets stretched further and further, redshifted, until it fades into darkness. The object appears to hang there forever, growing dimmer, redder, and colder, never quite crossing the threshold. From the falling object's own perspective, of course, it crosses and plunges inward in seconds. Two completely contradictory experiences, both physically real. This is one of the deepest paradoxes in all of physics, and even today, it remains unsolved. Welcome to the information paradox. But before we get there, let's talk about the structure itself. Because a black hole is not simply a point in space, it is an architecture, a layered system of increasingly broken physics. The outermost feature visible to us is the accretion disk, a vast swirling ring of superheated gas, dust, and shredded stellar material circling the drain at millions of miles per hour. The temperatures inside that disk reach into the billions of degrees Fahrenheit. The material glows so brightly across the X-ray spectrum that some accretion disks outshine entire galaxies, billions of stars, from a single region smaller than our solar system. The first image of such a structure was captured on April 10, 2019, when the Event Horizon Telescope, a planet-spanning network of synchronized radio observatories, produced a photograph of the accretion disk around M87, a black hole at the center of the Messier 87 galaxy, 53 million light-years away. That black hole weighs 6.5 billion solar masses. Its event horizon is 24 billion miles across, and even from 53 million light-years away, the asymmetry in the glow of that ring told us something remarkable. One side was brighter than the other because the black hole is spinning, and the side rotating toward Earth has its light amplified by the Doppler effect, like a sonic boom made of photons. Black holes spin. That matters enormously. A rotating black hole, described mathematically by what physicists call the Kerr metric, does not merely curve spacetime, it drags it. Picture spacetime as a thick fluid. A spinning black hole stirs it. The closer you get, the more that dragging pulls you into rotation whether you want to rotate or not. This effect is called frame dragging, or the Lentz-Thirring effect. It was first detected by the Gravity Probe B satellite experiment in 2011, confirming that even Earth, spinning slowly as it does, drags spacetime very slightly around it. Near a rapidly rotating black hole, the effect is savage. There is a region outside the event horizon of a Kerr black hole called the ergosphere. Inside this zone, spacetime itself is being dragged around faster than the speed of light relative to the distant universe. No object inside the ergosphere can remain stationary. Not a spacecraft, not a particle, not light. Everything must orbit. You cannot fight the current. You are carried, and still you have not crossed the event horizon. You are still outside the point of no return. That boundary, the event horizon, is not a wall you can see or touch. It has no surface. There is no gate, no sign, no membrane. It is a mathematical threshold defined by the Schwarzschild radius, the distance from the singularity at which escape velocity exceeds the speed of light. Cross it and nothing, no signal, no light, no cry for help, no information, can ever return to the universe outside. For Sagittarius A-, that radius is roughly 7.4 million miles. Pack 4 million solar masses into a sphere that small, and the escape velocity at that boundary reaches 186,000 miles per second, the speed of light, exactly. Physics draws a hard line, and the universe enforces it without exception. What happens inside the event horizon is where certainty ends and theory splinters. General relativity predicts a singularity, a point of infinite density, infinite curvature, where the known laws of physics break down completely and produce nonsense as an answer. Whether a true singularity actually exists at the center, or whether quantum gravity, a theory we have not yet fully written, replaces it with something else, remains one of the great open questions in science. What we do know is what happens on the way there. If you fell into a stellar mass black hole, one a few times the mass of our Sun, with a small event horizon, the tidal forces would kill you long before you reach the boundary. The difference in gravitational pull between your head and your feet would stretch you outward along the line of fall and compress you from the sides. The effect scales into something physicists call spaghettification, and the name is accurate. At the atomic level, you would be drawn into a long, impossibly thin thread of matter, molecule by molecule, atom by atom, until the atoms themselves were separated, and you became a stream of particles spiraling downward. But fall into Sagittarius A or M87, and the mathematics change completely. Supermassive black holes have enormous event horizons. The tidal forces at the event horizon of a black hole weighing billions of solar masses are actually quite mild. The event horizon is so far from the singularity that the difference in gravity between one end of a human body and the other, at the threshold itself, is manageable. You might cross the event horizon of M87 without feeling a thing. You would simply be inside, and nothing could ever bring you back. This is where the time story turns truly dark. From inside the event horizon, the singularity is not ahead of you in space. It is ahead of you in time. The future, for anything inside a black hole, leads inevitably and inescapably to the singularity, just as your future inevitably leads to next Tuesday, whether you want it to or not. You cannot avoid it by turning around, by accelerating, by any means known to physics. The singularity is your future. It waits. Now consider the opposite end of the story. What happens as a black hole ages? Stephen Hawking showed in 1974 that black holes are not permanent. They radiate. Quantum mechanics, the physics governing the subatomic world, requires that near the event horizon, pairs of virtual particles pop in and out of existence constantly. Ordinarily, these particle pairs annihilate each other immediately. But at the event horizon, one particle of the pair can fall inward while the other escapes outward. The escaping particle carries energy away from the black hole. The black hole loses mass. Over time, an almost incomprehensibly long time, it evaporates. The temperature of this Hawking radiation is inversely proportional to the black hole's mass. Sagittarius A*, weighing in at 4 million solar masses, radiates at a temperature barely above absolute zero, a few billionths of a degree Kelvin above nothing. The cosmic microwave background radiation filling all of space is far hotter, meaning Sagittarius A* is currently absorbing more energy from the universe than it radiates away. It is still growing, not shrinking, but the universe is cooling. Over a span of time so vast, it makes the current age of the universe, 13.8 billion years, look like a single heartbeat. The cosmic background will cool below the black hole's Hawking temperature. Then the equation flips. The black hole begins to lose more than it gains. It shrinks. As it shrinks, the temperature of its radiation rises. The smaller it gets, the hotter it radiates, the faster it loses mass, in a runaway cascade that ends, not in silence, but in a final violent burst of gamma rays as the last of the mass is converted to pure energy and the black hole is gone. For a black hole the mass of Sagittarius AS, that evaporation timeline runs to roughly 10 to the power of 87 years, 10 with 87 zeros. The current age of the universe expressed in years has 10 digits. We are talking about a span of time that cannot be communicated by any normal method of human counting. And yet, physics says it ends. Everything ends. There is something almost unbearable about that fact. A structure 4 million times the mass of our sun, bending spacetime, swallowing light, freezing time at its edge, bending stars in their orbits, and eventually, after an incomprehensible stretch of darkness and emptiness, it goes. The star S2 knows something about this. Orbiting Sagittarius AS on a tight, elongated path, it completes one full orbit every 16 years. At its closest approach, it swims within a few billion kilometers of the event horizon and reaches speeds exceeding 4,350 miles per second, about 2.5% of the speed of light. At those speeds and that gravity, both special and general relativistic effects become measurable from Earth. Astronomers watching S2 have confirmed the gravitational redshift predicted by general relativity. Light from the star shifts toward the red end of the spectrum as it climbs out of the black hole's gravitational well, losing energy, stretching wavelength. Physics, confirmed again at the edge of the most violent object in our galaxy. The event horizon is where known science ends and mystery begins. It is a one-way surface wrapped around an unknown interior. On one side, everything we have ever built, everything we have ever measured, everyone who has ever lived. On the other side, silence, inevitability, and a future that flows only toward the singularity. What a black hole eats is not just matter, not just light, not just stars caught in the wrong orbit at the wrong moment. It eats time. It stretches it, bends it, freezes it, consumes it, and at its edge, that barely visible ring of fire, photographed by 8 synchronized radio telescopes from across the surface of the Earth, we see not the black hole itself, but the shadow it casts, the outline of a region from which no information escapes, the silhouette of the end of time. And somewhere, 26,000 light-years from where you're sitting right now, Sagittarius AS is still turning, still warping, still waiting. So here's the question I want you to sit with. If you could stand near the event horizon and watch 1,000 years of human history play out in what felt to you like an afternoon, would you want to? Would you want to see how the story ends? Drop that in the comments. I'm genuinely curious what your answer is. If this blew your mind even slightly, hit that like button and share it with someone who thinks they understand how the universe works. And if you want to go even deeper, make sure you're subscribed because next week we're going somewhere that makes a black hole look predictable. See you there.